if it weren't for the Netflix TV series, I bet most of you would never have heard of the three-body problem. So what is it, and why is it so complicated? Well, first, let me try a simple analogy. A married couple are happy and living in harmony in their new home. All is going well until the meddling mother of one of them turns up to stay. The mother throws the relationship out of balance, causing arguments and chaos. The result is highly unpredictable, but the chances are one of the three won't be staying. And nobody knows which one it will be or how things will end. If you expand that to the universe, you have the three-body problem. On the celestial level, the mathematical problem is about predicting the motion of three bodies, such as stars and planets, affected by each other's gravitational pull. If we're honest, our math isn't up to it. Although researchers are working on it, we don't have a formula to take in all the variables needed for the calculations. It's probably best to go back to basics to understand why this is such a headache. In the early 1600s, German astronomer Johannes Kepler discovered what we understand today as planetary motion. He explained how planets, like the Earth, rotate around a star, our Sun. About 50 years later, Isaac Newton proved mathematically how planets revolve around their stars. His theory explains how a planet in an elliptical orbit moves faster when it comes closer to its star, and how long it takes to orbit. Newton's discovery is unique because he had to create his own form of mathematics to do it. That new mathematics is known to us as calculus, the torment of every high school pupil. Newton's theory perfectly explains how two large bodies will interact, influenced by their gravitational fields, such as the Moon and Earth. It also works for the Sun, Earth, and Moon, but that's really due to the Moon's mass being so small relative to the Sun and Earth combined. However, even Newton realized his theory didn't quite work when it came to the three bodies of the Sun, Earth, and Jupiter. Every time the orbits of the Earth and Jupiter lined up with the Sun, there would be a little gravitational tug on the Earth. This worried Newton. He thought that over time, these little tugs would eventually make the solar system unstable. But everything looked stable. So Newton had to come up with an answer. His best solution to the problem was that God intervenes and puts things right. Let's roll forward 130 years or so to mathematician Pierre-Simon Laplace. Born in Normandy, he's often seen as the Isaac Newton of France. He looked at the same problem and worked on getting God out of the equation. To do that, he developed an extension of Newton's calculus called perturbation theory. Laplace knew that even though Jupiter has a huge mass, it's far away. So the tug is tiny when the planets are closely aligned, and even less when they are furthest apart. So, crunching the numbers, Laplace theorized that over time, everything cancels out. Therefore, the orbits of the planets will remain stable. Phew, that's a relief. But elsewhere in the universe, things are not quite as rosy. It's estimated that up to 85% of the billions of stars in the universe are in binary or multiple star systems. And we know from Newton and Laplace that a couple of massive stars can live happily together in a stable state orbiting each other. But what happens if another star appears on the scene? How is it going to interact with the stable binary system? You could think of it like two magnets a few centimeters apart, and a third is introduced. Will the third magnet be drawn to one or the other, and as it gets closer, will the magnetic forces repel it in another direction? But what happens if those magnets were stars and weren't stationary but orbiting each other? That's a whole different ballgame. What the mathematics tells us is that the introduction of a third large body causes chaos. The motion of the three stars becomes random. There could be a collision. A star could be ejected, but there is no way of predicting the outcome. And that is the classical three-body problem. We can analyze where each of the three bodies are, but can't predict where they will go next. The slightest change in the original state can cause vastly different outcomes. That's what comes of chaos. I can hear Star Wars fans saying to hang on, but that isn't right. How come Tatooine in the first Star Wars movie had 2 stars? Well, that's down to what's called the restricted three-body problem. We don't have to worry when the third object is a planet with mass magnitudes less than a star. With a planet orbiting a binary star system and its mass so relatively small, it has minimal effect. If the planet's orbit is far enough away, it doesn't realize there are 2 stars, and it experiences gravitational effects that are as if they were just a single star. But if that little planet happens to move closer to the stars, then the restriction is lifted and anything could happen. So that's the basics of the three-body problem, and it's the same for 4, 5, 6, as many bodies as you want. Out in the universe, there are clusters of thousands of stars. We can watch them, and our mathematics can model what they might look like. However, we cannot track and predict where one star will be later in its journey. Efforts are underway to try to solve the problem, but none has yet come close to a solution. A group of European universities have started looking at neural networks to solve the puzzle rather than humans and supercomputers. They are working with what is known as the drunkard's walk approach. It's based on the idea that as a drunk walks in random directions, there is the same chance of him walking to the right or left. Then, it's possible to calculate the probability of a drunk ending up in any given spot later. The researchers are using this to assess a system in which a third body approaches the orbit of another 2. So, given the initial velocity of the body, the drunkard's walk framework told them the final state of the three-body system. It's a big step towards a solution, but there is still a long way to go before the approach can be adapted to a practical three-body system in which many forces are at play. As the author of the award-winning novel on the three-body problem, Louis Sitchin, puts it, the physics principles behind the three-body problem are very simple. It's mainly a math problem.
Remember to hit the subscribe button and ring that bell to stay updated with our latest content. And while you're here, why not check out another one of our exciting videos? Thanks for watching, and see you in the next one.